Okay, so welcome to this uh, series on probability in NLP, AI, and machine learning. So I think this is the 31st lecture, and we have Dr. Amar Azad and Dr. Rudra Murthy from IBM Research, Bangalore. So Rudra did his PhD from CPIL. Was my student working on multilingual named entity recognition. And Amar is with IBM and a collaborator for maybe now 3 years or so. We are all part of this IBM IITB AI agent project, which is a flagship project of IBM and IITB collaboration. And they are highly accomplished researchers with deep insight into NLP, machine learning, and the relevance of this topic is that large language models are doing wonderful things, and there is a kind of feeling that large language models would possibly revolutionize the way AI, ML, NLP is done. And language models, essentially, if you know, capture probability. So probability of the next sentence, probability of a word given the whole context, and so on. So this fits in the theme of our series on lectures in probability applied to AI. So that's okay, and we are very thankful to Amar and Rudra, describing this topic to us and discussing things. Okay, Amar and Rudra, over to you.
Thanks a lot, Professor Pushpak. Yeah, we are feeling honored actually to to talk about this. In fact, this is something which is very new to us as well. I mean, I think maybe very new to the entire community as well, but it is very promising area, and the whole idea is that we can bring in some kind of like insights and get some tractions of people around this. So as you so I'm Amar Prakash Azad. I am actually working with IBM for, as Saroj mentioned, uh, uh, for I think around 7 years now. And with me, Dr. Rudramurthy is there. Maybe Rudramurthy, you want to add some more things about you?
No.
Okay, so we'll be talking about this quite a few things in prompt engineering, and I think we'll be shuffling with each other. Uh, the more one of the thing which I would like to say before that, maybe this is something where we can make it more interactive. If you have any questions or anything, feel free to chime in between, and let's try to make it more interactive. And sir, please, if you have any comments anywhere, please add on to that. It will help all of us, including me, me and Rudra as well.
Sure.
Yeah. Okay. So with that, the plan is like that. So we thought actually this is something new area, and that also has quite a lot of things to talk about. So why not we should make it in a two parts. Let's have the first part, or maybe this time we can have some kind of like overview, introduction, what it is, how it is coming up, and why people are getting attracted towards that, and glance over a few recent literature. Let's get some basic methods and maybe some methodical approach to what is prompt engineering about it. And then with that, that will actually develop a good understanding for prompt engineering. Then we can go and deep dive some of the models, and most importantly, later on we'll go and look into some of the open research problems. Maybe we can actually try to look some of the problems and see if we can talk about that, and or we can collaborate on that. So that is how we thought, and we kind of divided that into two parts. So a few places, I mean, me and Rudra will be, I don't know, wherever required, we'll be chiming in with each other. But this part, I think I'll be talking a little more, and I'll let Rudra talk a little more in the next part. But we'll be mixing up each other everywhere. Uh, so so even before we start, actually, one of the survey paper is looks like very nice and very comprehensive kind of covering the entire area of this prompting, and in fact, a large part of what we'll be talking about this is coming from this survey paper. Of course, connected with many other things, but this is actually one of the basis of this kind of like we felt that this has got good coverage of all the work what is happening in this area. And in fact, these guys have actually maintained a nice website. This is from CMU. They have maintained a nice website actually where they're tracking all the recent papers and recent work and ideas and all those things there. I mean, one of the pioneer, one of the prominent professor, Professor Graham Newbig, he's actually doing quite a lot of work in this area, and his students are also like yeah contributing a lot in prompting. It might be good to see to his work in prompting. So let's start with the introduction of prompting, uh, what actually it is. And even before we go into that, let's think about and go a step back into NLP. How actually NLP has been, though NLP is not new. First of all, NLP actually is existing for quite some time. I would say even before I started working on some technical aspects of or maybe some engineering things. Even before that, NLP was actually quite much into focus. And IBM itself has quite a few, quite a few landmark things developed by a lot of researchers. Maybe I would say that goes back to some 20 years or even more than that before. But uh, if you look at that, I think what happened is that initially a lot of work effort has been done on something called feature engineering, and then from there develop some kind of models, and of course initial rule-based model, then some kind of uh, machine learning models has come up, and then the big change or big shift has happened once a neural network has come. I think we all have many of us has witnessed about that in something around 2015, when suddenly all this feature engineering work has all efforts has been started moving towards designing new architecture for neural networks. And of course it has it has gained a lot of attraction, a lot of work has started happening in that. But it was not even a few years down the line, by 2018, when after BERT paper has come, maybe around that time, BERT has actually triggered the wave, and then a big sea of changes happened. Then people have started like kind of not making new architecture, but rather developing things over some kind of standard architecture of transformers. And then people have moved into objective engineering kind of uh, uh, efforts. And this was a very big change. People call it sea change actually in NLP, and I think we all are aware of that. And 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 it is not, it is since last few years. I would say it's 18, 19, and it's like 4 years now, right? uh, I think almost everywhere transformer has taken over. Literally transformer has taken over. Nothing is beyond transformer is happening. Very minor work is happening beyond that. And 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 I think now, since last couple of years, people have come to the point where actually looks like their big another sea change is happening, that is prompt engineering. And I'll go in one by one of them. So let's see this. Let me just, sorry. Yeah. So this is what I was saying about feature engineering, where actually I think big focus was there towards supervised learning, and that was of course before neural network. And the whole idea was that design some kind of features based on data, based on task, and then actually after extracting the feature, which a lot of effort has been used to be put in, and then come up with some kind of models, machine learning models like SVM, CRF, and so on, and then solve the task. And many of times actually they are like one solution, one task, I mean, many times it's not also very much widely around wide range of data sets, but this is the kind of like era that was going on. And then with the neural network, actually the shift has happened, though it started from Mikolov's, which the great work of Mikolov from word to wake, which is 2013 around that time, and that took around 5-6 years. But I think the main I mean, the focus has shifted around 2015 onwards. And there we I mean, the effort has been completely moved from from feature engineering and to some kind of like network design, and we started leaving all the feature engineering aspects on a neural network itself. So network itself figure out what are the features. Let's design a new network, new loss functions and things like that. But most effort were put in to how to design a new network for different tasks. And a new network, I don't mean just like that, but basically more efficient networks for the task to be uh, solved. And their efforts are mainly put around what is the right sort of like embeddings what we can get, and then fit it well with the task and so on. And we have seen a lot of things around that, CNN, LSTM, and all sorts of network there. And this is the transformer era. And there, why people call it big C change, because before that, actually, we were trying to train network most of the time. And here with the transformers, what has happened is that many things got changed. First of all, the architecture got changed. So architecture almost started with a few architectures only. We were kind of fixing them. Okay, so I mean, some set of architecture for classification task and all BERT kind of models, for generation task GPT kind of models and things like that. Only a few handful of architectures. But and on top of that, we were trying to kind of like do mostly to fine tune them, or maybe even if you are trying to pre-train, but with very specific kind of pre-training, not like every time we are pre-training for that. So this is why actually, I mean, the community says, I mean, that this was a big sea change. And and I think many of us are aware of that. And here, which is we are in this next big sea change, is prompt engineering, where we are actually going along with that. And the kind of changes what is happening here is that uh, so, so this is started by the way from 19 onwards. and and what has happened in last 4 or 5 years is that a lot of language, good quality language models has been built bigger and bigger. And those language models are almost like captured enormous amount of information, maybe, I mean, very loose sense, you can say, like words information into it. So why to actually uh, the effort is, I think the idea here is that why not use that language model itself, and let's not touch it. Let's leverage the language model. And we can, to leverage the language model, we will need to do something on top of that. And that is where the prompt engineering came in. So let's design some kind of like prompting, which actually we can prompt the language model and ask it to say something. And these promptings most of the time actually textual, because we understand them well, but need not to be textual actually. And we'll be talking in some of the I mean, recent literature, what different kinds of prompt people have been exploring, and what potential prompt one can explore further. uh, uh, Sarup is asking
Sorry,
for.
that went by mistake. Sorry.
Okay, okay, so I'll decline it.
Yeah.
Okay, okay, no problems. Okay, yeah. And I think there are a few models now in place. One of the very prominent model for prompting actually has come up as GPT-3, because it is supposedly a few months, still few months before, it was one of the best model. But I think last few months, quite a few models has come up, like Bloom, and Big Science has come up with some model. OPT has come up with some model. And like a lot of other models are coming, which can be, which could which models actually could be some of the candidate models for prompt engineering. I think the problem with GPT-3 is that we don't have access to the model. We can just use them on some pay-to-use basis. But this is where we are.
And
So having that,
Google has this Palm model.
yes, sir. Yeah, yeah.
Yeah.
Thanks.
Yeah.
I think quite a few model. I shouldn't. I would say put them in the list. Yeah, quite a few models has come in the last few months. Yeah. So with that, let's start with what is prompting actually. So as we just discussed about that, the prompting is basically to encourage how to use a pre-trained model to make a particular kind of prediction what we want to have it. For example, like if you look at this, right, this thread. So we wanted to have like, okay, let's say what is the best word actually we can complete this sentence with. So JDK is developed by, and a model, because the model has seen a lot of text during training, so it can actually fill in with that understanding that Oracle might be the best fit. So here it's something we all know about this. This is kind of like close masking kind of prompting, where actually we mask something and ask them to fill. Another prompting could be that you have a text and ask that to summarize, and maybe you just give a prompt which could be like TLDR. Here actually is again about that, but this Bernie, I mean, the Ernie model actually does a different kind of prompting, which is very much close to like what we have seen in masking. So different ways actually prompting can be done, whether before or after. Sometimes we can do before also text, and then we ask the model to actually fill it up, and that filling it up is happening most likely based on the what is the best probability in probability, what is the best text that it model thinks that it can fill it with based on the knowledge. So let me give some examples to you, and I'll ask some of you to actually let me just pull up some of this. I'm sure many of you would have you have tried these things, many of you would have done, but let's have a fun time here. So I've just pulled it up, one of the model from one of the simple language model from LNLP, and a couple of more we'll see. So this is a simple kind of uh, prompting, right, where we actually fill the sentence. I just wrote it myself here before. So let's say that while most birds can fly, some cannot, such as. And this is a mask we ask the model to fill in. And when we ask him to fill it, sorry, what actually, okay, let me figure it out what it means. Model output. Sorry, I think I chose the wrong model based text token.
I think you should check the mask language model from the left sidebar.
Yeah, sorry, yeah, you're right. Thank you for that. So I think I took the classification model there. Mm-hmm. Okay. So yeah, here. So as you can see, this is this MLM model. This actually gives you that humans is the best fit with this mask. And interestingly, if you change slightly, I will say slight change. Let's remove this dot here. This prompt actually makes the model to do something else. So apparently it looks like prompt. What is the right prompt? That's very important for even for in these simple situations. Let me put it back and let me just forget about this comma here. It will again do something wrong. You see that, right? So I mean, it looks like the model actually model has been trained, but apparently all these language model are slightly sensitive to the kind of prompts what we give them. I mean, this is one of the very contrived example, but yeah, please go on.
Pardon, Nomar. I have one question. Why do we call this as prompt? This is just a mass language modeling. Like we're asking for the answer in the place of mass, right? For prompt, we need to give some examples to the model. Okay, these are the perfect examples. What can be the output for the current given input? Isn't it?
That's a very good question, actually, Nihar. So prompt is more, when I say prompt here, prompt is more of a generalization of different types of prompt. One of the prompt type, what you have just not told about that, we can actually set a sentence before that or later,
Yeah.
which are called different prefix, postfix, this kind of prompt, and we'll be coming to that detail slightly later on. But definitely, this is also one of the prompt which is called close prompt, close type of prompt.
Close ones. Okay. Okay.
Yeah. So I just wanted to give this because I think many of you would have used that, right? Many whoever works on transformer, they would have used it, and we clearly notice it here just to motivate that the right prompt is very important. Despite this is one of the very simple example, right?
Actually, the terminology is little different. We used to call it as closed task. Now they're like putting it as closed prompt. So yeah,
Yeah, I
little
mean
bit confusing because
there are
of
quite a
this.
lot of overlap here there.
Yeah,
They
yeah.
might not be changing the meanings, but I think the whole I mean the calling prompt is just bringing into another one set of umbrella and put them methodically that these are types of things there. Of course, this has not started. See, I wouldn't call it like this is something completely new. This has started sometime a new set of work where we are trying to use the language models. And I mean, there are multiple ways you can use the mask. You can use masks for even fine tune the model, pre-train the model. But when we say prompting, we are generally trying to not to do any of such tasks. We are trying to use the language model, not to change the language model. Does it make sense?
Yes, yes, Amar.
So this ML, when you say you use the word MLM, right? The MLM is mainly used for pre-training the model, basically building
Yeah.
the language model. And we are going
Yes.
into a kind of like paradigm where we don't want to use the language, we don't want to train the model. We just want to use whatever pre-trained language model, basically use the information what you have from there.
Yes.
Right. And I think in a similar line, I just wanted to give another example, and this might be slightly interesting and more funny. So sorry for
M stands
boring
for
here.
what? In MLM, what does M stand for?
Mask language model, sir.
Okay.
So there are 3-4 types of masking people do. One is, I mean, for pre-training, one is MLM, even for translation language, TLM, and sometimes people call it CLM also, causal language model, but that is mainly for autoregressive kind of.
There is
Yeah,
another called PLM also, probabilistic language
Yeah.
model.
no, but what is most popular now is LLM, large language models. So I thought M stands for medium language model or something.
Yeah. So, sir, those all things, large language model are just telling about that this is a model, but all the words which we used before, the type of training basically. So MLM is a, I mean, type of pre-training basically. MLM, CLM, PLM, all those were actually about how do you pre-train the model.
Right.
Or sometimes fine-tune also. And in fact, that time they call it continual pre-training, which, I mean, quite a lot of overlap between the terminologies, but this is how it is. These are, yes, sir.
Okay, thank you.
Yeah. So this might actually might be something interesting. So I think this is one of the very GPT-J by Ether AI, which is a very small GPT. Not you should not be comparing the performance of this with the GPT-3. This is just 6 billion parameters, but it does quite a lot of things which actually GPT-3 does. And let's do so. I think one of the very good quick example which we have seen just now is summarize and TLDR, right? That is a simple prompting, very simple example of prompting. So maybe let me just pull it from some text from here. Let's say ICICI Bank, or maybe I don't know. Let me pull it from here. Okay, I had done this, so let me just pull it up. Just before this talk, I was trying some examples. Let me go there. And you all, I mean, this is open, so you, it is not allowing me to put everything. Let me just put a small things. Just a moment. It is not allowing me to copy the text from there. Can I do this? No. Okay. For some reason, they don't allow me. I think this is a problem with the websites. They don't allow to copy the text from them. Okay, this is some text at least has come. So maybe this text we have entered. I don't know how this will do, because as we have seen that that they are very sensitive to the text as well as the set of prompts. So unfortunately, in this case, it has almost copied, pasted all everything, but with some other some more information actually. So ICICI Bank has reported a growth. Okay, so so it has tried to summarize this. ICICI Bank has reported a growth on this. And that is something called a zero shot prompt. So where actually TLDR, because the model has seen already TLDR, so it is able to directly summarize that. Let's see this. So this is actually, it is one type of prompt where we are asking the model, giving some examples. So this kind of question I'll give, this kind of answer I want. So gives a few examples of that, and then ask the model to give, can you give me the answer? So it's like on the fly, or maybe in this is called prompt augmentation kind of methods, where actually we in prompt itself we provide them what kind of answer I want. So I just gave him, so he understand that, okay, when I say France and I'm asking for Paris, and there's a relationship between them based on a take, but the language model itself figures out that what is the relationship between them. And then next time onwards, we ask him Sweden, then it is actually giving me Stockholm's and all. That is very, I mean, that was something interesting to me actually looking into. And of course, it keeps on giving quite a lot. Sometimes it does mistake also. And actually, have you guys, anyone has tried that, these kind of things?
Yes, Amar, I have tried, but I am still unable to figure out why TLDR works in the summarization task.
Okay, so why TLDR works in summarization? The answer would be not very difficult, because when the model was getting trained in many text, you would have seen that on some of the web page, right? There are a lot of text, and then the web page itself writes, okay, in TLDR, the small summary is there. So somehow model has seen that when you give a good amount of text and then after text you have TLDR, then you're actually having the short summary of that. So it kind of understands that relationship. It's based on the
So
training,
you are
during
saying
training time.
in the data set for the self-supervised training of the large language models, TLDR was were present before the short summary.
Right.
Okay.
So because
Okay.
of that, language models have already understood that, and that is why these are the reasons why large language models are getting very famous. Yeah, Rudra, you wanted to say something? Please go ahead.
Yeah, but sorry, Amar. So adding to your point, these large language models are able to generate simple translations. And one of the primary reason is I just pasted a link to a web page where you can see small conversations. I mean, day-to-day conversations uh, translated from Hindi to English. So when the model sees such examples during pre-training, it remembers it. And then when you ask the model to generate few translations, it's able to recall, and that's how you see the model is able to also generate translations. So Amar, in this query, right,
Yeah,
if you generate 10 translations from English to Hindi, you'll be able to see such examples.
yeah. Right, right. So that's a good point, Rudra. That's a very valid point actually. And it actually, so I was going to come to some next examples what Rudra is saying now. I think does it make sense to everybody? Some who was sorry, I couldn't
So,
didn't see the name.
Aman, so all these 3-4 tasks that we show, all of them are closely tasked zero shot learning.
Yeah, you can call them zero-shot learning. In fact, there is some different nomenclatures are there, but it's okay. You can call them zero-shot learning.
So when you presented this QA with that country capital thing, right?
Right,
So
right.
probably it has seen some listing like this during training, and that's how it has arrived at the right answer. Is it like that?
Yeah, that is one way of explaining that. And I am slightly hesitant to say I would have told very, very boldly that this is exactly what happens there.
Right.
But I'm going to break that thought in a minute, and that is
Okay.
why I'm not so boldly telling that.
All right.
But
All right.
that is very much right.
Okay.
So far, that's the concept that actually the model has seen that kind of data, that kind of relationship in the data, and that is why it is able to understand that and does these things.
Okay.
And that's very, very correct, because really that kind of, I mean, that is some of the papers they have explained also that why these models are able to do these kind of tasks, right?
Right.
And I think let's have that. Okay, let's till this minute I'll say yes, and we'll move forward, because I think in the next minute I'm going to break this completely apart. So
Yeah.
this is fine, right?
Yes. Good.
So far.
Yeah.
Okay, and in the same line of this, right? I'm just going to say one more example, and I think you all see that as a human we understand what is this question, what is the answer, and so does this. You will see the language model also understand what is the question, what is the answer. We are so far so good. I think the language model is doing as good as human, right? And the explanations just now we had, that is also fitting well with this. Everybody is fine with me so far?
Yes.
No answers.
Go.
So very recently, actually, we were discussing some within our organization here, IBM itself, and we figured out by some of our colleagues something which I'm going to show you now. So let me do this. Let me add some kind of random text here, which the model would have never seen. And you see what I've done before everything. I've made something called, I don't know, people call it like egg language. They've added here 4 words in front of everything. Question also, answer also. And if I wouldn't have explained you this, right, the 4 word is there by just looking at that quickly, can a human does it, right? I mean, what would you expect from the model? And now you see the answer here. And this is exactly what I was trying to say, that I'm going to break this assumption that actually model has seen this kind of data before, and it is able to actually produce because it has seen before. But you can look at this, right? This kind of data it has never seen before. But still it is able to figure out that what is the relation across them. I don't know, my hypothesis is that because it has seen a lot of misspelling as well, so the model has learned how to correct and basically correlate the right spelling to that. But it's just my personal hypothesis. I'm not very sure how it does, but it does.
So Amar, here
Maybe
maybe that word piece tokenizer is probably playing a part here.
yeah, I was
Yeah,
about to say that.
yeah, I completely agree with that. But I'm saying one step further. That is where word tokenizer is doing that. But after that,
Right.
how that establishes a relation across the words and then the answers. That is because during the training time also it would have seen this kind of like problems where misspelling and all those things would have happened, and possibly that makes it that way.
How about actually wrong prompt in in wrong example in the prompt? Let's say for the capital of France, instead of Paris, we'll write something else.
Yeah. Can you do that?
So
Let's
I'll
say.
leave these exercises on you guys and
Okay,
come up
okay.
with
Okay,
that for the
okay,
next time.
that
So
makes sense.
next
Okay.
time we want to hear from you different kind of exercises. What happens? I mean, I
Okay.
can tell you that model actually many times you will see that model actually does this kind of things. But maybe if you guys can come up with some more examples, it will be very interesting to see what happens, and that will be really revealing quite a few things. Somebody else was asking some question in between. I think I cut them across. Was this sir or somebody else?
So can we tell that it is doing a few shot learning instead of zero shot learning?
I couldn't get you.
Can we say that it is doing a few shot learning instead of zero shot learning? Am I audible?
Yeah, you're audible. So let me put this way, that I think whatever way you give the name to that, right? There are quite a few things in that. When you, I mean, it's just a matter of nomenclature, right? So a different setting you can call zero shot differently. So I think here in this case, we will actually, there's a specific name for this. It's called prompt augmentation basically. So it's not even it's zero shot prompt augmentation. But you will
Maybe
find
to
a
answer
different
this
variations of that.
question, Amar, maybe to answer this question, there is no learning here. So it's
Yeah.
just engineering, prompt engineering. There
That's
is
exactly
no
what I was
specific
trying to say.
learning.
So I was not trying to get into the nomenclature. Nomenclature you can have. I mean, that actually changes slightly here there, but it's okay to call them that way, and
I
that's
mean,
okay.
this looks very much like that discussion of manifold hypothesis in computer vision. You give a few images of some kind or some type of the painter, and then the GAN generates images of that type of the painter.
Well, I mean, I think that's very different than this. Actually, there you're asking GAN to actually, basically, your GAN is actually taking a manifold somewhere else, right? But in this case, you are not at all touching the model. So you see that that's very different thing. There you are doing, there you can call it few shot learning. Basically, you by putting that examples, right? You're asking discriminator to do something different, and GAN takes the model somewhere away from, and in the right direction in some sense, right? So you're actually moving the model. So few shot learning is happening, but not here, right? Here we are not at all touching the language model. There's no touching happening. It is just that you give an input to that and it gives an output, and model is able to figure, basically based on the prompt you are getting the answer, and that is the reason, and that's exactly is all about prompting. That's why it's so attractive. That's why it's so important, and I think that's why we all are talking about this now today. And I will not go further examples, but you can do many sorts of examples. You can do all kind of things, and you see that a lot of magic happens. And as I requested you all, if you can come up with some few examples, some interesting examples, it might be good to have, and we can discuss more on that,
Uh,
right?
Amar, just one question. This one. So, so the examples that we looked at now, it was some sort of facts based example. So have people tried like common sense reasoning type of prompts?
Well, there are a lot of work. There are some work in common sense reasoning also. I'm not very sure we have in our slide. I will have to check that. But there's some very little work, one or two work has happened in common sense reasoning, and that's quite feasible. That makes sense because the language model has seen quite a lot of data in common sense, so it's possible to actually use them in that direction as well. But you have to accordingly do the prompt, and I think now going down the line in few slides, you will be trying to establish the foundations, what actually prompting means, and what are things you have to think about when you do prompting.
Sure. Yeah. Thanks.
Okay, so I think that sets quite a few things here with all of us, right? So let's see that. Just try to basically summarize all of these things, right? So I think one thing is I mean, we have seen that the paradigm, we have just talked about the paradigms from the perspective that what kind of like task has been done during those paradigms, but look at this kind of learning what we do during those paradigms, right? So before neural network, basically what we're trying to do is that we were doing definitely, I mean, most of our tasks, I wouldn't say all tasks, definitely all sort of works were used to happen, but the idea was that actually uh, non-neural network kind of language model, but they were getting trained based on the data, and from there doing feature engineering and all those things, right? Then after this neural network came, and there also similar kind of things were happening, but the efforts were there actually towards architecture design. But we were trying to get based on the data and based on tasks, we're trying to basically improve the language model or train the language model. With this pre-train and fine tuning, what has happened that we're still trying to. So by the way, so there is no arrows you can see in the right hand side, right? So that clearly means that actually they will not. I think you will need. I mean, here language model were quite loose in the sense that actually they are quite a bit of task dependent in the first A and B. So it was very difficult to establish one common thing for many different tasks or many different data set also. So they were like quite tied with each other. With this C, when we have transformers, then actually it so happened that now we wanted to have like one language model, but let's tune that, or maybe pre-train or fine tune that slightly with respect corresponding to task, but not too much. Don't change architecture. I mean, nobody change architecture much actually, and even a training task, only fine tuning task, and that is a time where actually semi-supervised kind of fine tuning and all those things happened based on slightly based on different tasks, but they were on the same model. So model was getting learned about all the tasks. But with this prompting, what is happening? Let's not touch the language model. Let's use that and put all the effort on designing this prompt for different tasks. So you see that there is a complete shift of the focus has happened here. Now we are not going to put any effort on language model. We are so far till this point we were putting effort on language model, improvement of language model. Now we'll not put any effort on language model. Rather we'll put effort somewhere else and use the language model, because language model, there are a lot of effort has been put already to develop as strong as possible language models, and this will keep happening. It's not going to stop at this point. So let's focus more on how to actually use them as we keep moving forward. Yeah, somebody has some question here.
I had a
Okay.
question. So in that
Yeah,
diagram, what was CLS and tag, like the relationship? LM was language model,
classification
right?
actually.
Okay.
Yeah, that just means the classification. So by the way, this picture I have taken from this paper, and I encourage you all to actually just look more details about that. So for your answer to answer, these are different tasks. So this is classification task, this is tagging task, or we call it I mean, sequence tagging tasks, and this is generation task.
Okay.
Sorry
Okay.
about that. I should have told it before. Yeah.
Yeah.
Please ask if something I would have overlooked in the slides. Then yeah. So I think right now here. So I think now moment let's go into that prompting basics. So I think we are very clear that okay, during supervised model, what we're doing that we are having a data and we are trying to train the model theta based on what output we wanted. And in the prompt based learning, the attempt is to circumvent this training of theta. Let's not do that. So instead of learning, instead of learning a language model. Sorry, here some typos here. Learning a language model of text X itself, use this distribution to predict whatever our desired output is. And I think I'll skip this. I will not go too much into it, just to tell that. So we are actually trying to go into designing a prompt function here in prompt engineering, such that given input text and given prompt what we want to put it either before or after, we'll see that where we can put for different tasks, what kind of output we want. I mean, the kind of output we want, accordingly, we'll put the prompt here. So we are actually looking into how to design the prompt and where to put the prompt, so that actually whatever task we have at hand, we can achieve that with a given language model. So that is the effort we will be doing, and that is why we call it prompt engineering, and different types of prompts. So so I think now we have and the prompt are typically textual prompt, but need not to be textual prompt, and that also we'll see some examples going down the line. And so what is the general prompt, general workflow will happen in this kind of, so workflow actually for prompt engineering. So I think naturally one can think that we have to add a prompt into our text. And that actually will give some answer, but we don't know what answer it will give. So then once the answer prediction happens, and you want to actually, sometimes you want to map that answer to something, some corresponding task. For example, let's say sentiment classification, that it might give some answer which is not actually in terms of sentiment. Some words we might actually want to map that also. So I think typically these three were key parts that will come into prompt engineering. And so I already had slides for that. So when I say addition, so we can have a template. That is one way of doing this. We can have a template, and one for the prompt and another for the answer, and fill in the input slot. For example, here, if you look at that, right? So if suppose input text is, I love this movie, we can have a template of this form where we prefix a prompt here. Sorry, X is, sorry, I think there was some mistake in, let me correct myself. So X actually is a text, and this is a prompt what we have. Overall it was, and then we put some, in this template, we have some kind of like blank space Z. That blank space is being filled by the model. So this is a template kind of prompting. And once we do the prompting, actually the output of Z that may, let me see first output here. The output of Z that might come here, which I was saying in the answer predictions, that is coming through the model. So language model is actually giving you, based on language model, that gives you the corresponding answer for Z, and that model may be giving you fantastic here. And now we are in the second part, and then we actually have to map this output to some class level if we have a sentiment classification kind of task, let's say. Then we want to actually map this to this fantastic to positive. So this could be one of the very simplistic way to look at the workflow. And then, so with that understanding, so let's have also look of what kind of prompts, typical prompts actually we can have. Something called filled prompt, where actually we have a text and we want to fill it up. Just now what we saw. And we can also have something called prefix prompt, where actually we put the text of our requirement before the prompt, and this might be the jet might be filled by maybe a sentence or maybe a few words or things like that. And one of the prompt which I think most of us know is close prompt, right? Which was MLM, which is this kind of prompt. Actually, I wouldn't call it prompt, but this kind of situation this kind of setting is used in mass language model training. And these are some just capturing all of them. So for like classification task, so this for this text, the template is the movie is, and this basically the idea is that how to come up with this text, the movie is, that should be corresponding to the input text and so on. And in the topic modeling kind of prompting, you might have to do something similar, because these all are classification tasks. They text span kind of things, where you want to have multiple words, where again it's very much similar to that, but the functioning is slightly different, where you are predicting not one word, you are predicting multiple words there. And I think these all kind of settings already we have people are aware of when they were working with transfer models for different tasks. So yeah, that's a high level understanding of all different types of prompting, what in a very simple sense what can be. So what kind of design consideration we should have for prompting? I have a quick question. How can we? I was thinking if we can have it like 20-25 minutes more today. Is it okay? So that we can have a right point to stop it.
Yeah. So maybe another 10 minutes. We can continue with the lecture in the next session.
Okay. So what are design consideration one can put for prompting? And I think the first thing first comes with what are the pre-trained model that you might want to choose from, then the prompt engineering for that, and then the answer engineering for that, and then expanding basically we'll go to that how to expand the paradigm for that, and then some training strategy for prompt. So these are things actually we want to go. Let's see how much we can cover in next 10-15 minutes, possibly one, possibly 2 or 3, and rest will continue in the next day. Yeah. So I might be slightly faster now onwards, but please feel free to stop me, and if you have any specific question. And the reason is that many of things you guys would have known already, or things like that. This is pre-trained model choice. So the first thing, so there are multiple pre-trained model that you would have seen before. I think people would have seen like left to right. And let me just go one by one. So left to right models, which are generally used for autoregressive kind of models, mask LM model, which is bird type model, prefix LM, which actually has a mixture of both of them, and encoder decoder are generally for where we have input text, and decoder is some is a text generation task, but depending on that, for example, like summarize and translation, things like that. So I'll kind of like very fastly move through these slides. And left to right model are like GPT-2, GPT-1 family of models. And of course, a lot of work has been done on this, like PLM and all those things. And the idea is that we just look, I mean, the prediction of the next word happens only based on the past words. Mask LM, where actually we have bidirectional attentions. So you look both directions to predict the word, and we all know about the bird. Prefix model, where mixture of things can be done, where actually for some part of a text we look in both direction, and some part of text to generate we actually look only in the past. And there are a few models for that, UniLM and ERNIEM. And encoder decoder models such as BART and all, where we have encoder separated, and then that is and the encoder output are attended to the decoder to generate the next text. And T5 is one of the very recent and very powerful model for that. So having that understood, what kind of model we should choose, and these are the names of model. I think I was kind of like skimming through them, so let's not go into that, because I think many people might be knowing about that in detail. I'll just let me skip through that. MLM T5. Okay, so which kind of model we should choose for which kind of task? I think these are very intuitive. So for conditional text generation or translation, conditional text generation such as translation, text summarize, and all those things, we can use either prefix LM or encoder decoder based kind of model for prompting, or even for generation like task where it is not purely generation, but in today's paradigm it has like information extraction and question answering. Similar models can be used. And here comes the most important part, where how to actually do the prompt engineering. So there are a few sort of work, and this again is the diagram right hand side is actually taken from the same paper, and they have quite a nice table of this. I mean, very nice set of tasks that is arranged together very nicely. I encourage to look into that. So with that, let's get into this, how to do prompt engineering. So I think the difference between the traditional formulation and prompt formulation is quite obvious. In traditional setting, we know that what class we want to, what we have in the given class, and we want to output in that set of classes. But in prompt, we actually have a middle step where we get the output, and then we want to map them into the classes. So the first we do the prompt engineering, and then after answer engineering that is happening. So for the first part where you do prompt engineering, so the first question comes, how to define a suitable prompt for that? Because that will depend a lot on quite a few things: data set, kind of task what you have at hand, and accordingly. So the idea here is that I mean, based on the kind of work what has happened in the last couple of years, is that first define the shape of the prompt what we wanted to have. That is depending on uh, task at hand, and then once we have kind of like frozen the shape of that, then we search what is the appropriate template we should choose for that. let's see some examples here. So the first is obvious thing, very well known, close prompt. So for so the shape is almost decided before first of all. If we decide that we want the output in the form of some word, then we choose a shape for um, close prompt, and if we want to have few words possibly, then we want to have like a sentence corresponding to uh, the prompt what we want to give, and then possibly what we'll do is we will call it prefix prompt. So the idea is that we should have the entire prompt before the text. So let me see what I mean. Where is examples? Let me just copy some examples first. So I think I think I'm missing an example here. It'll come in few slides, but let me clarify a little bit more here. So we'll choose a prefix prompt where the input text comes entirely before the output what we wanted. So for example, like we are given a text, I love this movie, then possibly corresponding to that we might want to create a prefix prompt, and this is the prefix prompt that will come in. Overall, this movie is, and then possibly Z might be filled in, though it looks like same, but the entire text is coming before the entire prompt that will come before the text what we want to be filled in by the language model. So that's why this is called prefix prompt. And since this is there, we can have like one or multiple sentences, possibly one or multiple words, or possibly full sentence. Obvious choice is that we'll go for autoregressive models such as T5 or possibly BART or GPT, things like that. Now comes the question that how do we design the prompt template? So obviously the most understandable way to do is that we can handcraft that, because that is something human can understand very well. So we kind of like configure the manual template for that, and then possibly in that we will search some of the prompts which are more suitable for that based on some formulations, whether we can have a set of manually set of prompts, and then from that set of prompts we search and optimize what is the best prompt. Or we can also have some kind of like automatically created templates, and from that we search. And so that search, actually we call it discrete space search, because we have a set of templates there. But we might actually see that I should call the other way around, that actually this, because we are constraining the set of prompts by defining uh, whether it's manual prompt or automatically generated prompts. There is some set of prompts. So because a set is restricted or constraint, that those might not be optimal prompt. So possibly one can go into look in the wider space of prompts, which may be in continuous space, and that might actually give us some different set of results. And I think it's obvious, intuitive to think about that in continuous space prompts, you might be getting a prompt which might give you better output or maybe optimal output. But it might come to the situation that human might not be able to understand what is this prompt. That might be just some kind of like embeddings only. And we'll be seeing some examples for that. Some examples for handcrafted kind of like prompt generation people have done. These are by Petroni et al., where they've created manually based on some non-domain experts actually have created some set of prompts. And also Brown et al. Has created a prompt for different kind of tasks, but they are also more or less created by domain experts. So having that understood, now I think the more bigger question comes, how to mine the prompt. So let's say that this is the kind of situation you have. I mean, for the question of relation extraction, and let's say that if we have a text, this kind of form of text, that Barack Obama was born in Hawaii, and different kind of text might be there in your data. then possibly one might think that maybe was born in this kind of form of prompt might be optimal, given that you actually would be able to extract X and then you ask them to generate Y. And I think the question here is that what is the right set of was born in that you should get based on data set? Or for a dependency parsing kind of situation, if you look at, then because the capital is actually dependent, the France is dependent on, they actually, in simple sense, I would say they actually depend on different set of words. Then what is the right set of prompt that you should have based on the data set? So what Jiang et al. Has done is that they have come up with some mining the right set of prompt for corresponding to a data set.
So Amar, can we continue in the next session?
Yes, sure.
Mhm.
I was just thinking that I'll just give 1 or 2 slides more, so it will actually kind of give an idea about that, and then I'll close it.
Sure.
Maybe just 2 minutes more.
Yeah.
I'll not go into that because this is an extension of that. I think what I wanted to say is that this work where actually there's something interesting, more interesting things are happening here. This is more or less searching the prompt, and we will go a little bit more in detail of that. But quickly, before we close this, just see here that we wanted to get a prompt for this. The question here is that given an original input X, whether it's a positive or negative, that's what we wanted to have. So what is the right set of prompt we should put in between that for the corresponding mask, we should get some output which can be mapped easily to the positive or negative classes. And it turns out that when they did the optimal search of prompt through gradient based search, then there's some kind of text that has come in between which might not make much sense to us as a human. And this is called like atmosphere allowed dialogue clone totally. It is completely irrelevant to us, but it so happened that based on data set and based on the language model, these prompts turned out to be optimal for this task. So this kind of situations where we see that these are automatically search prompt, but this might not be making sense to human. But and that is how one can search the prompt. And contrary to that, you might also want to have a prompt that actually might make sense to you. And we can discuss more of that in detail. And just quick counter example of that in continuous space. So in one of the work actually, what by Lee et al. And Lester et al., they have slightly different methodology, but almost similar kind of task. And the idea here is that you have, say, let's say you have a transformer model here, and what you wanted is that you want to you say, let's say that you want to do summarization or for the input text, what you will fit in here, and summary for that should come in. So instead of looking into this discrete set of prompts which are like text tokens, why when text token itself is not making sense, and that's kind of like extending the idea is that why not we should look in continuous space. So actually they kind of like prepend the transformer with some linear some layers, a few layers, and those layers they just optimize only those layers for the summarization task for the given data set, and they figured it out that they actually get some embeddings which are optimal to provide the summarization. Though the embeddings, the embeddings what they get in those prefix or prepended embedding layers, which acted as a prompt to them that may not actually make much sense when they tokenize them out and looked into the what token actually that correspond to. But those are the ones which are actually optimal. So there are some examples of how actually you can do the prompt tuning or prefix prompt tuning. So I think I'll stop at this point, and we'll continue the discussion a little bit, going more deeper into some of the work and getting into that. I mean, the idea was so far was that actually to give you some highlight overview of that, and then we'll go deeper into some of the text.
Okay. So thanks a lot, Amar, Rudra. So we'll continue 2 weeks later on Saturday. Okay, this time Saturday there was a problem. And I'll also show you some examples of prompt engineering where I took declarative sentences. So Ram is good, is Ram good? So, some of these interesting examples of, I'll not discuss anything, I'll just show you some of these examples and see what you think about these examples. This is done by Google's Palm, and some of my students are in Google, and they have, prompted, they have got these prompts from me and took these test sentences. And there are some extremely good outputs, but interesting cases of failure. Okay. For example, there is this famous sentence, buffalo, buffaloes, buffalo, buffaloes, buffalo, buffalo, buffaloes. Okay. So I'll show you this. So there are some 8 buffaloes in that sentence. So there, it doesn't produce anything. It just repeats the same sentence. So I'll show you those things, and maybe your insight will help in analyzing them. Yeah.
Sure, sir. That will be great, sir. Yeah. Sure.
Okay. So thanks everybody, and please join next Saturday. Yeah.
I think I didn't let Rudra talk today. So Rudra, next time I think I'll put you forward to talk more.
Yeah.
Sorry about that today.
You'll have to prompt Rudra.
Yeah. Sure.
Thank you. Bye.
Thank you very much.
Thanks, everyone.
Thanks.
Thank you, Amar sir and Rudra sir.